Thank you, Emmanuel, for this very kind, too generous introduction. And thank you to the organizer, Lucia, Emmanuel, and Juan for the very kind invitation. Today we'll speak on a recent joint work with Philippe Gravja, who is at Cergy University, which is in the north of Paris. It's called CYU University now. And Elliot Pachery. Elliot was a PhD student of David Chiron and Pierre Raphael in Nice, in France, and he's now a postdoc with Nader Masmoudi at the Abu Dhabi antenna of the Courant Institute. And part of this work was finished after his we studied it after his PhD thesis. So it's about Ginzburg-Landau equation, which Emmanuel mentioned, but it's in its most simplest setting, in a sense, so in the plane. So I will look at the Ginzburg-Landau equation written here on the whole plane. So the domain is R2 and psi is a complex function. Okay, so this equation has been very much studied, in particular by all the school and since the work of Bétuel, Brézicélien, mostly in bounded domains, but the fundamental solutions I will be interested in today most are naturally arise in the context of the whole plane. So this equation has trivial solutions, which are the constant solutions, so either 0, which is not an interesting solution that we see from a physical point of view, and the constants which have modulus 1. Okay, if you take a constant of modulus 1, and this is 0, and therefore this is a stationary solution. But there are other interesting solutions that have a topological degree, since we are going from R2 to the complex. So in a sense, you can think also of it as a function from the complex to the complex, or from R2 to R2. And so there's a notion, if psi does not vanish, a notion of topological degree at infinity. And so these are special solutions, which I would call vortices, which have this form. So the psi is this capital VD here, and there is 1 for each value of D in Z star. So when D is equal to 0, this is simply the constant solutions that I have already mentioned. So they have a profile, which is real, rho D of R, and they behave like exponential of I d theta. So they have a degree D at infinity, and the profile just needs to solve this nonlinear ODE so as to be so that VD is a solution of the Ginzburg-Landau equation. So this ODE was studied numerically in the 90s with a great precision on the asymptotics and so on. And the result goes as follows. For each value of D, well, first, maybe let me mention before mentioning that there is so these are solutions, but there are symmetries in this equation. So if this equation is invariant by translation, by rotation, and it's also invariant by phase shift. So if you replace the psi, how this works, let's see. If you replace psi with exponential I phi times psi, where phi is a constant, is a constant. Sorry. In R, then you still get a solution. So these are the symmetries of the problem, and so from this solution you can build a different one. But so if you fix the for example the 0 at 0 and the phase be trivial at infinity, but, and you solve this ODE, you get the following: that if you have a solution, a unique solution that joins 0 at 0. So this is the R variable, the radial variable. You have a unique solution that joins 0 to 1 at infinity, and 1 being the other constant solution when the phase is fixed to 0, like that. And for each and it behaves like that. So close to 0 for D equal to 1 or minus 1. Well, first you see this equation is invariant D or minus D. So let's assume from now in the talk that the degree is chosen to be positive. Okay, so it will be like a constant which can be computed times R to the power D. So here I've written for D equal to 1, and it has an algebraic decay to 1 at infinity. 1 minus d square over 2r square, and you can compute additional terms here back. So that was done by Chen, Elion, et Cui. And if you shoot if you shoot above that solutions, then the ODE will blow to infinity. And instead, if you shoot too low, then the solution will converge by changing sign, will converge to 0. Okay, and then you get by symmetry plus changing sign, you have the same situation when you shoot in the negative. But so the outcome is that there is a unique radially solution that radially equivariant solution that joins that connects 0 at 0 to 1 at infinity. Okay, and this is so this is for the profile, and then if you want to see it in the complex plane, then you just multiply it by this exponential I d theta. Okay, so these are called the vortices, depending on their degree. Okay, so associated to the Ginzburg-Landau equation, there's an energy, the Ginzburg-Landau energy, which I have written here. And the fact is that these vortices, the nasty thing about that is that they do not have finite energy. So if you write the gradient of Vd after this ansatz here, well, you get the derivative with respect to the radial variable here, and here the derivative with respect to the in the direction of the theta variable. And since these two vector fields are orthogonal, then by Pythagoras, if you compute the gradient square, and then I will integrate it on a ball of radius r because it's going to diverge, then I have the square root of this one and the square root of this one. And it happens that due to the asymptotics for rho d, so rho d is going to 1 at infinity, but sufficiently fast. So this term is not going to diverge when capital R tends to infinity, but of course this one is going to diverge. Okay, if you replace rho d by 1, then you have the 1 over r times d square. So if you compute the part of the kinetic energy which is due to the gradient of the phase, then you get this divergence, the pi d square times log of the cutoff that you have taken here for the ball, plus something that can be precisely computed, but which I have just written as capital O of 1 here, as capital R tends to infinity. Whereas, so as I already said, the part which comes from the gradient of the modulus and the potential energy here, these ones remain finite. Okay, so they can be integrated up to plus infinity. Okay, so this is one thing. So about so from now I will concentrate on the case where the degree is 1. So the rough idea, and this has been proved in different settings in the literature since the 90s, is that for d equal to 1, the vortices should be stable, whereas for d larger than 1, starting from 2, they should be unstable. So you can think of them as particles, and when and the degree as charges. And so when you have a multiply charged particles, it wants to split into many simply charged particles. Okay, it's energetically more favorable. And so since the energy is infinite, as I said, you can, at least from the beginning, try to work with the notion of a locally minimizing solution, and so you could define it in this way. So you say it's a solution on the whole plane is locally minimizing if you make a compact perturbation. Here I took a perturbation which is H01 in a ball of radius r, but this is compact perturbation. Then you can just you cannot decrease the energy. Okay, so psi is locally minimizing is if whatever epsilon the energy, the Ginzburg-Landau energy on a ball of radius r for any r is larger than what it was for your original solution. And it was proved by Mironescu in '96, by Petru Mironescu, that the vortex V1 is a locally minimizing solution, and not only it is locally minimizing, but it is the only one, which is not constant. Up to the symmetries of the problem. So the translations and the constant phase shift that I have already mentioned. The rotations and for vortices, the rotations and the phase shifts are the same. So they give the same thing. So I will only speak about translation and constant phase shifts. Okay, so more than that, so locally minimizing solutions need to satisfy this hypothesis. Okay, because otherwise they would not be minimizing. And what Mironescu proved is that, well, first, solutions that have finite potential energy necessarily have a well-defined degree at infinity. So there's no notion of degree. A solution could vanish very far away if you don't impose some restrictions on its energy. But if its potential energy is finite, then there are some, at least for solutions, for sure for solutions, you can define a degree at infinity. And what Mironescu proved is that the only solutions, not only the minimizer, but solutions that have finite potential energy and that are solutions on the whole plane and have degree 1 are necessarily equal to V1. So it's in a sense, it's a symmetry and uniqueness result. Let me mention that, yeah, proving symmetry for solutions, even for minimizers of variational problems, which are vector valued, here complex valued, is not an easy task. Many of the classical symmetrization arguments do not work. And for example, I should mention, I didn't wrote it on the slide, but the equivalent of this problem, of this theorem of Mironescu on a large ball instead of R2. So if you replace the minimization, this locally minimizing property by the minimizer on a big large ball, then you need to impose some boundary condition. But say, for example, you impose EI theta on the boundary of a big ball, then the fact that the minimizer is the symmetric one is still an open problem. Okay? So symmetric questions for, at least for large balls, symmetric questions for vector problems sometimes can be tricky. And okay, so that's well. And another open problem still is that when d is larger than 2, then it is known that well, the fact is that it is not known if there are other solutions than the vortices. Okay, the vortices, there is no good notion of, there are no minimizers, as I said. But if you try to devise or renormalize energy and want to minimize it, the minimization problem is degenerate, and probably you will have two vortices that go to plus infinity. But it is not known if there could be other solutions that minimizing one, and this is still an open problem. So solutions that have finite potential energy, that have a degree which is larger than 2, and that are not radially, that are not equivariant. Okay, so this is an open problem. So this is a uniqueness and symmetry result. Associated to this was a theorem about stability, because this is nice, but if one wants to study evolution equations, not just the stationary Ginzburg-Landau equation, but as Manuel mentioned, either the Gross-Pitevsky equation or the parabolic version, the parabolic Ginzburg-Landau equation, coercivity estimates for minimizer is an important question. So it turns out that also Mironescu, actually before his theorem about uniqueness, studied the stability of potential solutions and he proved the following. So you consider the again, since the total energy is infinite, you need to do something. You cannot write the energy at first. So here you are just going to look at the Hessian. You take perturbations that have, what he did was to take perturbations that are compact supports, again in a ball, and you formally, at least, you write the Hessian of the energy. In that case, it's not even formal if you work in H10 of BR, and you develop in terms of epsilon, and you get this quadratic form here. Maybe I can just well, explain the relevance of this term. The fact is that the equation, the energy, many of the terms are quadratic, so it's not complicated to compute the Hessian, but the the tricky term in some sense for the later analysis is the potential, which is where the real nonlinearity comes from. And so when doing some perturbation, you would like to look at things like 1 minus, you will have to look at this thing here, squared, and what if I just expand this, and I want to keep the V1 square modulus, I would have a minus, I will have a minus 2 epsilon V1. So in the whole talk, this bracket here would be the scalar product in the complex. Okay, so the real value of first one times the conjugate of the second one. And I still have the epsilon to the square here. Okay, and I need to put a square. And when you expand this, so this would be the potential. When you expand, well, you have the zero order term, which you don't care about. There will be a linear term, this one with this one, which will vanish because which will cancel with some part from the expansion of the kinetic energy here, because V1 is a solution. And you are left with the square of this one, okay, which is present here, and this one with this one when you do the double product, which explains the reason for the appearance of this term here in the quadratic form. And what Mironescu proved is that this quadratic form is coercive in H10. But what you can also easily show is that the coercivity constant, I will always call coercivity constant such that some quadratic form is larger than this constant times the norm square. This coercivity constant must go to 0 as the radius of the ball go to infinity. Okay. So what Manuel Del Pino, Fellmer, and Kowalczyk studied in a later analysis in 2004 was to analyze this quadratic form here, capital B, not with compact perturbations, as it is written here, but in the natural space for this quadratic form. So they defined the Hilbert space, we call it HB, the space naturally associated to the quadratic form. It has the exact same form as the quadratic form here, except for the sign. Here you have a minus sign, which makes it, otherwise this is positive. This is a non-negative term, this is non-negative. So, and capital V1 is between 0 and 1. So this is the negative, the bad guy in the quadratic form. So they define the norm in the space, the square of the norm with a plus here. So this is the natural space associated with the quadratic form. And what they proved is that this quadratic form is positive semi-definite in this space, and they compute, and its kernel only contains the real multiples of the infinitesimal generators of some of the invariance groups, so of the translations. So dx1 v1 and dx2 v1 are natural are naturally in the kernel of this quadratic form because of the invariance of the Ginzburg-Landau energy. You compute in the direction of some of the invariance, so it's 0. There is a third invariance, as I said previously, regarding the Ginzburg-Landau energy. It's the invariance by phase shift. Okay, so if you do a phase shift on V1 and look at the infinitesimal generator, so exponential I, and you differentiate, so that would be I times V1. But V1 tends to a constant, to 1, well, to modulus, it tends to 1 at infinity, and so it's not a good decaying function. In particular, it's not in this space HP. Okay, so that's the reason why you only get that it is semi-definite here. It doesn't come with a coercivity constant, but still what they were able to show, and this was important for a lot of work on desingularization for on perturbative methods, is that they have a Fredholm theory. They have a Fredholm theory. In particular, they can solve let me call LB the linear operator associated to the quadratic form B. So they can solve LB of epsilon is equal to a forcing term F, providing this forcing term is a little bit more decay at infinity than what comes from the space HP. So if F solve this, if F square is has some decay, so 1 plus norm of X 2 plus some positive number, let me call it sigma. If this is finite, then plus some, of course, you need to be orthogonal to the kernel. So if F has more decay like this, you can take its scalar product not only with so if F d x1 v1. Sorry. So this is now here I write this is the scalar product in L2. F dx2 v1, and you also put the orthogonality with respect to I v1. Now F has sufficient decay so that this has a meaning. If this is 0, then there exists a solution. And there exists a solution. Let me call it epsilon naught with a good estimate. So epsilon naught in HB square is less than a constant. So the thing times this thing here. Okay, let me call it norm F star. I think they call it with star in their paper with the square, and this is the norm F. Okay, plus all solutions are of the form epsilon plus all solutions in HB are of the form epsilon plus the elements in the kernel. So dx1 v1 plus beta times dx2 v1, and not this one because this one is not in the kernel. So there's a Fredholm theory, but it implies more. I repeat myself, more decay on F than what you get in the.
So sorry, can you explain the quadratic form B and the scalar product in Hilbert space HB? Is it the same or different thing?
Oh yeah, sorry. So here is the norm. So the scalar product. It's the natural one. Well, you replace an epsilon with an F and a G, and I only wrote the norm square. I'm sorry. Is it okay?
Okay, but scalar product is positively definite. It's not semi-definite, huh? If it is scalar product in the Hilbert space.
Yes, but okay. As I said, there's a difference between. So this is probably the computer. Here there is a minus in the quadratic form.
A minus.
The difficulty is to show that this one is
I see.
Is positive. This one is obviously only has positive terms. Okay. So the difference between the norm and the quadratic form is here. Okay. So this is not a problem. This one is a good it defines a norm, and this is a real Hilbert space. Okay, but the quadratic form is not the norm. Okay.
Okay. Thank you.
Sorry, I forgot to mention that. I should be more. Okay. So let me show our functional framework. So I will introduce this space, which may look kind of weird, but I will try to explain you that it isn't. So I will not speak about perturbation for the moment, even psi. And so I wish to convince you that this is a good space to study the problem, the perturbation of V1. So the reason for this, you see here, I'm multiplying. So it's a norm which is not invariant by translation, because it implies V1. It wasn't either in HB in the previous slides. So somehow the issue with the vortex, as I said, is that the gradient squared is infinite. So what you do here is that you multiply by the the complex conjugate of V1. Somehow you remove the phase at infinity, so that this field outside times the complex conjugate of V1 has degree 0 at infinity, and you require that one is a finite gradient. Okay, and but then V1 is 0, close to 0, so this does not give you control on psi close to 0, so you add a term which will give you a control on the gradient of psi close to 0, and it's convenient to multiply it by this function here, which is 1 close to 0, and then decays at infinity. I'll show you why. So this is also a Hilbert space. There's not much control at infinity, so the function in this space, maybe I can mention, for example, that H would embed even in a compact way with on weighted L2 space, where you would put things like that. So psi squared over, and here you need to put something which is more than so x squared at some power s, say with s strictly larger than 1, but not 1. Okay, and then you define the energy space, well, energy. As the functions in H for which the potential is finite. Okay, these conditions ask that the potential is finite. And what you can say, for example, is so this is a vector space. This is not a vector space, of course, because of this condition, but it is the natural space, the natural energy space for the vortex. So here you can say, prove that, for example, it's included in L4 plus L infinity. And another important feature of E is that if you add an H1 function, H1 of R2, then you remain in E. So it's equal to E. Okay, and then you can define a distance in H, which is well given by the norm in H, but you add the L2 distance between these nonlinear quantities of psi1 square. So these two are in L2. So when you take the difference, you can take the norm in L2. And this makes it a complete metric space. Okay? And the first nice thing about this functional setting is that now you can define the renormalized Ginzburg-Landau energy in this way. So you take the Ginzburg-Landau energy density on a ball of radius r, and you remove the one of the vortex. This is one possible choice. And the proposition said that this quantity then is well defined. And it's important to do it this way and not the other way around. There are some papers in the literature where some people try to introduce a space by requiring something like that. But this is not the good, I believe this is not the good way to do, because in some sense, this quantity here, this condition, this being finite, enforces the degree 1 at infinity. Whereas this, okay, for fields capital psi that are good behaved, somehow also tells that you have degree 1 at infinity, but you could have a field capital psi that has degree 0 at infinity, but that has some oscillations, so that this limit would exist, but psi would not be of degree 0. So the correct way to do it is to first define the space and then show that this renormalized energy is finite and well defined in the space. And the other thing is that the vortex V1 is the unique global minimizer. So this is the extension in a sense, or say just the translation of Petru-Mironescu's result in our setting. So this is about the functional setting. And then the theorem is the following. The main stability result is that the energy is coercive for the not the norm, because it's not a norm base, but for the distance square. So it's there are symmetries. So you cannot hope that V1 itself is that there is coercivity without a condition around Z1. So what you do is you have to define the orbit, the orbit by the symmetries of a function, in particular V1, but here of a function psi, which is just all the functions that you obtain by translation and phase shift. So this, if psi is in capital E, is in the energy space, so all this manifold here lives in the energy space. And what the theorem says is that the energy any function is larger than this little constant times the distance to the orbit squared. Okay. There's something that may look strange if you are used to translation invariant problem. Usually you would put the orbit here on V1 and then psi to the orbit of V1, but it's just a small peculiarity due to the fact that the norm is not translation invariant. So this norm, you see, it's adapted to look at functions that have somehow their zeros close to 0 because you multiply by V1 bar. So it's important to compute the distance between the orbit of psi and V1 and not the contrary. So this is the theorem, and now the energy is a natural quantity for evolution problem, and so not too complicated consequence of this theorem is the orbital stability of the vortex. If you consider, if I have time, I will go back with a slide on that. If you consider the Gross-Pitaevsky equation, it turns out that there's a notion of there's a notion of a Cauchy theory in our space capital E. So there's a solution psi t, and the theorem says that if your initial data psi naught is sufficiently close to for the natural distance dE to the vortex, then it remains so for all time, not to the same vortex V1, but the orbit. This question of orbital stability. I will comment later on the fact that is there a possibility to improve that to something better than orbital stability. Let me go on for the moment. So this is the result, and there's also a way to modulate the solution close to the orbit manifold. Since if you are sufficiently close to the manifold corresponding to V1, so to V1 and all its symmetries, then you can define somehow, in some sense, the closest point on the manifold by using a translation A of t. And so this is for the solution, a translation A of t and a phase phi of t. And what you can show is that the speed of the vortex and of its phase are small if you are sufficiently close to the manifold. This is the weakest thing that one could expect. Probably one would like to show that that A of t tends to a constant as t tends to plus infinity, some kind of asymptotic stability that could hold, but we are far from proving that for the moment. You cannot just say that the speed is small. This is expected since it is a stationary solution, and the divergence of the phase also here is small, but we have no more than that. Okay, a few words about the idea for the proofs and how we relate it to earlier works. So first, to motivate the introduction of the functional space is rather easy, or I will go in reverse. Let me just expand this quantity by Leibniz rule and the square of the sum. So here square plus double product. And so reminding the definition of the what I've called the renormalized Ginzburg-Landau energy as being a difference between the energy of psi and the energy of V1. Here I just wrote it for the kinetic parts. It's the only one that has infinite, and whereas there's the issue of the well definition. So this term here, you see, I just split into two, the part here and the part which is here. Okay, I split the 1 and 1 minus V1 square. And the same for this one. I split it between this one and this one, and I keep the double product. Okay, so I want to prove that this, in the end, I want to prove that I can integrate this on R2. Okay, it's not going to be Lebesgue integrable, but I want that the integral on a big ball tends to something when the radius of the ball tends to infinity. So these first two terms here, you see, these are precisely those of my functional space. So by definition, they are integrable on R2. This one is easy because let's see. This is maybe I should go quick. This one is in L2. because that's the potential energy, and V1 is okay. This term is not in L1. That's the trouble of the vortex not being finite energy, but it's smooth. So it's in any LP with P strictly bigger than 1. In particular, it's in L2. So this product here is integrable. It's not an issue. And there is this this tricky term here, where there will be some cancellation phenomena. So we're going to split it into two. So let me remind you what I wrote before. The gradient, if you look at the gradient of V1, okay, so we had the gradient of the profile, ρ1 prime times x over modulus of x, and there was the sorry, the ρ1 x perp over x square, and I add the I, and times exponential I theta. Okay, so somehow this is the bad guy at infinity, the one for which the energy is infinite. So we are going to remove it from the gradient of V1 here. Okay, so here I have a gradient of V1. There's a bar. I put it after. I add and subtract this part of the term. Okay, and there's the issue of this singularity here. So forget about this for a while, but this is just a cutoff. So chi r is a cutoff, so that this only lives at infinity. So chi r here in the sequence, say chi r is something which is like that. Okay, so you cut between, say, r and 2r, and this is 1, this is 0, and this is chi r, and in radial. So this is a function of the radial variable. Okay, so now you see this term here as the derivative of the profile, so it's something that is a good decay, and it's no problem so this whole function here is integrable on R2, and now I have this one, and this looks very much like in NLS equation, like a momentum. So this is I times, let me call all this capital U. So this is I U gradient U. Okay. And the lemma is the following. So now it is multiplied by this function, contrary to NLS, x perp over modulus of x, is that this thing, when integrated on the ball of radius r, it has a limit. And not only it has a limit, but it's going to be, because you see it's a quadratic quantity, it's going to be small with respect to the distance from psi to V1, and small in terms of this cutoff capital R. Okay, what you can easily see is that if you replace psi by V1, then it's identically 0, because V1 times V1 bar is the modulus, so it's the profile, it's a real. So it's gradient of something real against I times real. So this is pointwise 0 when you replace psi by V1. And what you can show is this this kind of smallness. Maybe, yeah, I showed it a fake proof, but it explained well why it is so. So if psi times V1 bar, so the reason of multiplying by this V1 bar is to kill the phase at infinity, to kill the degree at infinity. So now in good situation, psi times V1 bar, you can hope that it will have a modulus and a phase, a real phase. Okay, it's not true in general, but let me explain the fake proof like that, at least sufficiently far. Okay, and so the first thing that you can do in that case is rewrite this term by removing a 0. And the reason for this is that, okay, the reason for that I can put this here is that with the 1, this is equal to, the term that I'm adding is equal to a divergence. 1 minus chi r squared x perp over x square phi. Okay, this one here is equal to this, because when you put the divergence of phi, it is exactly the term that you get here. When the divergence, when the gradient goes here, you have a gradient of a radial function dot perp. So this is also pointwise 0. And when the divergence goes here, this is a divergence-free vector field. Okay, so you can put this one. And once you have this, you see that this term is like the potential. So this term is going to be in L2, and this term is going to be in L2. I'm cheating a little bit here, but it's part of the gradient of this. You see, the gradient of this will have the gradient of the phase, and since this is in L2 by assumption in our space H, you get the L2. Now you have a field which is decaying, a cutoff, and that explains the 1 over R. Okay. So the actual proof goes by an argument by mimicking an argument by Patrick Gérard in decomposition in high and low frequencies. So the outcome of this is that we have decomposed the energy in this way. So contrary to this decomposition, where was that? Sorry, I've lost it. Okay, so this was one possible decomposition with B and the cubic term. Now we have this decomposition here, and here I have voluntarily kept in the splitting of the potential term. I have voluntarily kept this square, which is non-linear quantity, but it is a square. In particular, it is positive. Okay, and so this is what you get when you make the difference between module square of V1 and the module square of the V1 plus its perturbation. Okay. And okay, so we have this, which comes from this fake momentum, or okay, momentum with this x perp over modulus of x square, and this is a variation of the old B, where there is the reminiscence of our cutoff. So in particular, you see the cutoff happens here in these two places. So if I want to make a link now with the quadratic form capital B studied previously, this is what I would obtain. Maybe I can keep both. Yes, exactly. If I develop eta squared here with this definition, you see, here I will have a quadratic quantity, and I will get B. Okay, so the equality is B is equal to this. But if I do that, I'm back to the situation studied by Del Pino, Fellmer, and Kowalczyk. We have this, but the fact is that the higher order term, the cubic terms, they cannot be controlled by B. Okay, so you cannot control in the end the energy using the coercivity of capital B. So we should not do that in order to have a nonlinear coercivity. So what we do is we go halfway. We split, so we have this eta epsilon squared, okay, which is what is left from our potential, and in some sense we would like to keep it because it's a quadratic term, it's a positive, okay, but it's in terms of a nonlinear variable. It's not adapted to the linear theory. So we cut it into two. We split again. We divide the space into local and infinity. Okay, this will be the part at infinity. It will be kept out of the linear analysis, and there is the local part. Okay, and for the local part, I split eta epsilon according to epsilon. So I do a classical linear analysis. So I get this term here, which is reminiscent of one of the term in B, but it's only localized, and everything else I leave it in something that I will call a nonlinear term. Okay. And so in the end, I have this splitting now of the energy, a quadratic form, a nonlinear term, and this quadratic form, which I'm going to keep away. So I'm going to treat this term here, which was reminiscent of a momentum. In the end, it will be absorbed by whatever I can say on QR, on my quadratic form we're going to study, and the nonlinear term. So in principle, it's a quadratic term, but at infinity, and we are going to absorb it because it's not appropriate. There's no linear space appropriate for this. You see, it was only defined through the integral, the limit of integral of a quantity. So it was not adapted to a linear analysis. In the end, it will be treated as an error term. And so the result about the quadratic form is the following. So now it's a quadratic form which is well defined on our function space capital H. And if you impose the three orthogonality conditions corresponding to the three invariances of the renormalized energy with So this chi here is also a localization cutoff. So it's chi 1 if you want. So that we use the standard L2 products here, but we could use different orthogonality conditions. Then QR is a coercive. See, but there is a slight technical annoyance, is that we cannot fix R independently of epsilon. I will explain that in a moment, but it's not important in the end. Okay, you need to fix it between a constant which you give yourself and a universal constant times this one. And the reason is the following. Let me, yes, I can finish with that. Okay, so how does it come? Well, the problem is naturally decomposed into orthogonal Fourier sectors. This was done already in earlier works, and it's because of the form of the quadratic form. It's useful to write it in this way, so to shift the sectors by 1, because somehow it will be symmetric with respect to ei theta. So I write it as ei j plus 1 theta, and j is in z. And then the quadratic form naturally splits. So the Q part is block diagonal in each Fourier sector. So here I have written A and B as the real and imaginary part of the perturbation epsilon. So this one is really a block diagonal. And the mixing between Fourier sectors is in I because of this, where was this I? Okay, see, because here there is a square of a scalar product. So for example, if you have a cosine here, you get a cosine square, so a mixing between constants and cosine 2 theta. And so this mixing is reflected here. It turns out that the zero mode is rather easy, and it does not depend on our cutoff. So it's exactly the same as in the analysis of Delpino, Fellmer, Kowalczyk. It can be written as the integral of a non-negative term. So it's non-negative. There's something in the kernel. Here you see in the kernel you have the constants of the profile. So one will be killed by invariances, and the other one will be killed by this part I. Okay. Also, for large Fourier modes, the quadratic form is easily shown to be positive, because then the gradients become the dominant part. And the tricky Fourier sectors is j equals 1 and minus 1. So which is in original Fourier sector is 0 and 2. So the constants and the exponential of 2 I theta. And what we do in that case, that's where our cutoff is an important. So we have to compute terms like this. Okay, so E and F would be either the real part in the A1 in the 1 sector and minus 1 sector, or the imaginary part, and that will change this plus into this minus. But the point is that we split that. We have divided it in such a way that you are going to write our quadratic form as a mixing, in a sense, between a local quadratic form, which is the original one studied by Delpino, Fellmer, Kowalczyk, and a quadratic form at infinity, where our cutoff has removed this momentum time terms. Okay, and it cannot be exact, so there is an error which you obtain when you replace one quadratic form by a sum of 2 quadratic forms, because you do a cutoff, and there are gradients, so there are some error terms. But so this Q-lock is exactly the one that was studied by Delpino, Fellmer, Kowalczyk, and in particular we know its kernel. It can also be written, that was a very nice thing, it can also be written as an integral of a non-negative quantity, but in a matrix form here. And so we know its kernel. And the Q infinity, that one is really easy to analyze, because it's made of positive terms. If you go sufficiently far at infinity, you see this at infinity is going to behave like 2 over r squared minus, and this will be 1 over 2r squared. So this is positive at infinity. So at infinity, and this one also the same, 2 over r squared minus 1 over 2i squared. So this one only has positive term, and so it's easy to deal with it. But then there's the price to pay is where you do the cutoff. And that's where this constant capital N0 comes from. Somehow you are given a perturbation, you are going to choose the position of the cutoff in a place where it has not too much gradient by pigeonhole principle. And so if you have a coercivity for this and for this, in the end, if you choose well the place of the cutoff, you can forget about this term, and that's fine. I see that I'm going out of time. So this is the end of the idea of the proof, and maybe it's a good point to stop. And if there are questions, I will show more open questions, for example. So, but thank you for your attention.